jet type of questions, as in okay, application of Bernoulli's equation. Okay, Shivam will discuss. For example, if you have a situation like this, if there's any particular question, Shivam, you have a doubt, and you can just send it to me. We'll discuss that also. So we have a situation like this. There's a piston of area A on which we are applying some force. And then there's a small orifice over here. So fluid is coming out with efflux velocity like this. So you can see that the pressure at a point like this compared to the pressure just outside the orifice. Like this, okay. But V1 is very small compared to V2 because V2 is equal to the efflux velocity and the area of the orifice is very small, is negligible. Okay. And H1 is equal to H2 because it's the same level. So this kind of, okay. So this is an example of this kind of situation. Anybody else has any other doubt in hydrostatics or hydrodynamics? Okay, Durgesh has sent me a particular question. Yes, I will go through it. So this is a question from H.C. Verma. It is a variation of the standard Venturi meter. The difference here is for the measurement of pressure difference. There is a U-tube inserted into this. let's say liquid is flowing like this, and also the U-tube has mercury in it at the bottom. Let's say this is water. Because this here is mercury, and this height difference is measured to be h. Okay. So again, if we take this point as point 1 and this point as point 2, then so P1 plus half rho V1 square is equal to P2 plus half rho V2 square, where E1 V1 is equal to A2 V2. But before that, in this equation, rho is the density of water. So we have P1 minus P2 is equal to half rho V2 square minus V1 square. So that is half rho we can take V2 square common. We have 1 minus. Now this P1 minus P2 on the other side, you can see, is going to be the pressure difference between this point and this point also. Oh, sorry, the pressure at the point 1 will be more. So be the other way now. The level of mercury will be more on this side, less on this side. So the pressure being greater here will push the mercury further down. Okay, so now, within the mercury, you can see that this point and this point, let's say 3 and 4, have to have the same pressure. Okay. So pressure at the point 3 is P1 plus. So, I mean, from that you can understand that the pressure difference between these two, P1 minus P2, between these 2 points is equal to the density of mercury minus the density of water to G into H. So this has to be substituted here. Okay, so Durgesh, it's clear, I hope. Okay. Viraj, is it clear now?
Yes.
Okay. Piyush, you have some doubt in this question?
Sir, we could have also taken height जिधर हम लोग ने difference लिया है, where there also we can take the datum level ना, so 0.3 and 4.
Sorry, come again. We can take.
So the edge difference which you have given, sir, we can take that level also as the datum level ना.
At the what level?
Sir, the edge difference जिधर है ना, edge.
I'm not following what you're saying, Piyush. Yeah, the difference in the level of mercury in the two columns, that is because there's a pressure difference, no?
No, sir, where that edge you have drawn ना, sir, edge, height.
Yes.
हाँ, so the नीचे वाला जो bottom line है ना, sir, which you have drawn with dotted one. So that line can also be taken as a datum level, right?
Yeah, you can take that. We get the same result.
Okay.
You can take any reference level, it doesn't matter, but any 2 points within the same liquid at the horizontal level have to have same pressure if that liquid is not in motion.
Okay.
So that's what's happening to the mercury column. So you take any 2 points within mercury.
Okay.
Right?
Yeah.
Okay, so next we will do a couple of questions from the module. So exercise 1, question number 56 and 57. Just give me a minute. Yeah, so module number 4. Exercise 1 is on page number 116, I think. Yeah, so page 116 in module 4. So question 56. If you haven't done this question yet, just go through it. I'll explain. It says a horizontal right angle pipe bent has a cross sectional area of this much, and water flows through it at a speed of 20 meters per second. The force on the bent part of the water pipe is how much? Yeah, so this is a bit like reaction force concept. So let's discuss it. So this is in the horizontal plane. Gravity is going into the plane of the board here, let's say. Let's say we have some liquid which is flowing like this. Actually, it would not make any difference even if this was vertical, as long as the area of cross section is uniform. Just there's a difference of pressure if it is vertical, whereas if it's horizontal, then the pressure is uniform everywhere. So anyway, so this is a horizontal plane viewed from above. Okay. So what is happening is that you will realize that there is this kind of force, okay, because the liquid is applying this kind of force. So how to calculate that force? Let's understand. So you have liquid particle at the point here, let's say, which is having some speed like this, okay. And by the time it reaches a point B like this over here, speed becomes like this. So going through the corner, if you have a liquid section of mass dm, its momentum changes from v at a to v at b. So that is like this. So this is a change in momentum. So the magnitude of this change in momentum is so the force. So this is impulse. So force F is rate of impulse. So that is density into volume rate of flow. And volume rate is equal to area into velocity. So force, reaction force, in this case becomes this much. Okay, so in this case, it will become density of water into area of cross section 10 centimeters square into speed of flow, which is given to us as 20 meters per second. Okay, you can take root 2 as about 1.41. You get the answer.
So this question is from the module.
Yes, this is module 4, exercise 1, question number 56. Okay, so Shivam, hope this is clear.
Yes, sir.
Okay.
Sir, this equation will be applicable for each and every type of bend, na?
No, but the angle of the bend has to be 90. Agar angle kuch aur hai, then this factor of root 2 will change. You understood, na?
Okay, sir.
This is coming from this vector diagram, na? So this angle being 90 is important here.
Yes, sir.
Okay.
Sir, but
And
if the cross section area is also changed.
then the magnitude of V1 and V2 will change, V and VB. So for that you will have to use continuity equation.
Okay, okay.
So
Yes,
if
sir.
you have a uniform pipe bend at any angle theta, then you have to just change that angle from 90 to that theta in the vector equation. And if the cross sectional area is also changing, then the magnitude of V1 and V2 will also be changing, of VA and VB's magnitude.
Yes, sir. Thank you.
Okay. Next is 57th question.
Sir,
Yes.
can I explain this sum again?
Sorry, come again.
Can I explain this question again, please?
Yes, explained over here. As you can see, the liquid is coming through a bend of 90 degrees. So there's some reaction force acting on the liquid at the bend, which you can understand intuitively, because the liquid's momentum's direction is changing.
Yes.
So there is rate of change of momentum. So there's force involved. So that's how we are calculating the force. It is rate of impulse or rate of change of momentum. So imagine a particle of liquid dm going from A to B. How much is momentum is changing from? Initial momentum is this direction. Final momentum is perpendicular to it. So
Yes.
change in momentum from the vector triangle you have calculated. Is it clear?
Sir. V root 2, no?
Yes. So this is an isosceles right angle triangle. So the hypotenuse, which is the change in momentum, is dm into v root 2 because magnitude of v is equal to magnitude of v. Okay, so Shikhar, I'll come to your questions also. Okay, let's do question number 57. Then we'll come to your questions. So Piyush, hope this is clear now.
Yes, sir.
Okay. So question 57 says that a jet of water having velocity of 10 meters per second, stream cross section of 2 centimeters square, hits a flat plate perpendicularly with the water splashing out parallel to the plate. The plate experiences a force of how much? Okay, so again, this is a question of reaction force. And again, actually, the answer will be similar. So let's say this is a plate. And we have jet of water like this, let's say. Anyhow, so this is hitting this like this. And after the water hits, it goes off tangentially like this. So you have to calculate the, I think you have to calculate the normal force, right? So I think you'll just have to change the language of the question here. You have to calculate the normal force. So the normal force acting on the plate is the force in this direction. And that will be basically equal to this area of cross section is A, rho A V square. Because in this direction, you can see that the reaction force on the liquid is stopping the momentum altogether.
It will be like an impulse, right? But
Yes, it's like a collision impulse force.
can treat the plate as a heavy mass.
Sorry, come again.
Can treat the plate as the heavy mass, which will not
Yeah,
move. But
plate you treat it like a rigid body, which is connected to the earth or something, so it's stationary. So collision of particle with the rigid surface. Okay, if the momentum of the particle is mv and it stops as it hits the surface, so then it becomes the impulse becomes mv. So rate of impulse will become dm by dt into v na, and dm by dt is rho av.
yes, sir.
Okay, so now we will come to some more questions from the same exercise. Shikhar has asked question number 45 and 47. So let's go back to these. So 45 says an open cylindrical vessel 20 centimeters high and 10 centimeters in diameter. Circular hole with a cross section of 1 centimeter square is cut at the center of the bottom. Water flows from a tube above into the vessel at the rate of this much. Okay. Very interesting question. So let's understand this. So we have a cylindrical vessel like this. I'm just showing the side view of it. Okay.
This is which
And it
question?
has small opening at the bottom. There's a circular aperture at the bottom. And it also has some kind of an inlet pipe. So what all is given to us? Okay, so this is 10 centimeter in diameter. So this area is like this. Okay.
So this is which question?
This is exercise 1, question number 45. Yeah, so we have a 20 centimeter high vessel, 10 centimeters in diameter. Circular hole with cross section 1 centimeter square is cut at the center of the bottom. Okay, so this hole is having area 1 centimeter square. And this whole thing is 20 centimeters high. Okay, so now water is flowing into this. At a volume rate
100 cc per second.
of 100 cc per second. So see what happens is initially when the vessel is empty, let's say, as water flows in, the rate of efflux is very small because the height of liquid is very small. But as so basically the rate of inflow is much larger than the rate of efflux. But as the level of water rises, so does the rate of efflux. So at some stage, the two balance. The rate of efflux in terms of volume rate becomes equal to the inflow rate. Okay. So the speed of efflux here is this much. Then what is happening? The volume rate of efflux below, that is equal to A into V. So when the level of water, let's say this y, becomes stable. So at a steady state, so what they mean by steady state is that y becomes constant. So y becomes constant because the volume rate
should be equal to 100.
Volume rate balances the
yes, the volume rate of efflux equals to the volume rate of inflow from the tube. Okay, so this A into efflux velocity should become equal to 100 cc per second. Okay, so this A is 1 centimeter square, and this efflux velocity will be approximately root 2 gy.
Yes, sir.
Okay. Because as you can see, this A is very small compared to capital A. This is 25 into 3.14, so more than 75 times smaller, so we can neglect. So this is 100 into 10 raised power minus 6 in meter cube per second. This is 10 raised power minus 4 into square root of 2 into 10 into y. So this should be equal to 10 raised power minus 4 on this side. So that's it. Your root 20 into y should be equal to 1. So y should be 1/20th of a meter. So that is 5 centimeters.
Yes.
This should be the answer you should be getting.
Okay.
Okay, so hope this is clear, na, Shikhar?
Just back
Yes, sir.
Yeah,
of efflux.
yeah, Piyush, what were you saying?
I was just saying in this question you just have to balance the volume rate of efflux and rate of
Yes, yes. The level of water will become steady when the volume of water in the tank is steady. So that is when the rate of inflow is balanced by the rate of efflux.
Okay.
You can understand it. Okay.
Yes, sir.
Okay, next. So actually, in this type of question, you can do one more interesting calculation, which is a bit lengthy. If you assume at time t equal to 0, the level of water in the tank is 0. Okay? Y is 0. And that is when you open this inlet tap with
Yes.
uniform 100 cc per second. Then you can find the level of water as a function of time. So to find the level of water as a function of time, what we'll have to do is we'll have to assume at some time t, let's say the instantaneous level of water is y. So the rate of change of volume of water in the tank, that will be equal to the rate of the inflow minus the rate of efflux.
Yes, sir.
So this is a constant rate. Let's write that as n, where n is this quantity 100 cc per second. But this will be minus a into root 2 gy.
Yes.
And the rate of change of volume will be this. So we have this, sorry, a into y. Okay. So this we have this relation a into dy by dt is equal to n minus small a into root 2 gy. So if you solve this differential equation, you can see what is y as a function of time. But that's a more lengthy question in comparison. Okay, so you can try this out later. Okay, next we are going to discuss question 47. Same thing, exercise 1. Question 47 is like this. You have a vertical tank opens at the top. It is filled with a liquid and rests on a smooth horizontal surface. Small hole is opened at the center of one side. Area of cross section of the tank is n times the area of the hole. N is a large number. Neglect the mass of the tank itself. The initial acceleration of the tank is how much? Okay. So this is again based on that reaction force concept.
तो बट इसमें इम्पल्स को हम लोग मास इनटू एक्सेलरेशन को ये करेंगे ना इक्वेट.
Just reaction force, na, directly reaction force is equal to mass into acceleration because it's on a frictionless surface, so the tank will start sliding because of reaction force.
Yes, sir.
Just, so this being on a frictionless surface, now I think it says it has the whole halfway, right? Center of the side of the tank. So this dimension thing will become important. So this has an area which is the area of the tank divided by n. And liquid is filled to the top. So if this height is h and this is at the center, so it's h by 2. So in this case, the rate of efflux would be how much? It will be square root gh, square root 2gh by 2, like this. Okay. So what is happening? The reaction force that is acting on the tank will be this value, right? So this direct formula, Shikhar, you're clear with this now?
Yes, sir.
Okay. So that is the density of the fluid into area of the tank divided by n into gh. Okay, when you substitute this over here. So this reaction force will now cause the tank to accelerate backwards. So this should be equal to ma. Now mass of the system will take approximately, because you're neglecting the mass of the tank, as the density of the fluid into volume. So that is why all these things are not given to us in the question, because they cancel out. So, G. So the acceleration comes out to be how much now? Rho h cancels out, so it comes out to be g by n. Okay, so Shikhar, hope this question is clear.
Yes, sir.
Okay. Now moving on, question number 51. Yeah, this is also a very interesting question. So the background to this question is, what you have to understand is that if there's a tank of height h again, having an orifice at some kind of a depth or height, whatever, so if you have liquid up to filled up to the top, so this height is h, but the orifice is at some depth y, let's say. So what happens is that the liquid coming out here, what is the range it achieves? So because this is h minus y, the efflux velocity it achieves is root 2 gy. So the range it achieves is efflux velocity into the time of flight from here to here. So that is, it's falling through a vertical height of, so you can think of this thing like this into some time where that time is this much. So the range comes out to be, when you substitute this, h minus 1. So now, for example, if we have two holes which are cut such that they are having the same value of range, so if this hole is cut at h1 and this hole is cut at h2, you can see y and h minus y are interchangeable. So if r1 is equal to r2, it means that basically means that h minus h1 is equal to h2, or h2 plus h1 is equal to h. Now we also know that the range is maximum when it is equal to h for y equal to h by 2. So this maximum range so actually two things are combined in this question. One is that if you have two holes which are at heights h1 and h2, you can take the height from the bottom or from the top, it doesn't matter. Okay. But if they are having common value of range, then h1 plus h2 must be equal to h. So now if we cut a hole such that its height is at a position where we're getting the maximum possible range, so its height should be at h by 2. So in terms of h1 and h2, that becomes h1 plus h2 by 2. Okay, Shikhar, hope this is also clear.
Sir,
Yes, sir.
Okay, very good.
sir,
So let's move on to question number 54 next.
sir,
Yes,
what have you written as the formula for R? 2 root 2, 2 root
Jagannath, can
under
you speak a little bit louder, please? Beta?
in the formula for R, you've written 2 into root of what is that?
Jagannath, I can hardly hear you. Speak louder.
Sir, I'll type out the message.
Y into h minus y.
Yes, Jagannath.
Sir is asking what have you written for R is equal to 2 into root 2.
How R is coming as that? Okay.
No, sir,
So
he's asking what you have written.
he's asking
What you have written R is equal to.
R is equal to 2 times square root of, that is the range. It is equal to 2 times square root y into h minus y. That is coming from this projectile motion type of concept. No? It's like a horizontal projection. Where this height is h minus y. So if this starts from here at time t equal to 0, by the time it hits the ground over here at time t, what is that time going to be? It is going to be square root of 2 times this vertical displacement divided by g. So what is going to be this range now? It's going to be a horizontal velocity into time. Okay, so the horizontal velocity here is square root of 2 gy. Jagannath, is it clear now? That is how you got this range. Okay. Okay, so next
Sir,
we are
can
moving.
you explain the last step again? How did you get that H1 plus H2 by 2?
H1 plus H2 by 2. Okay, because see, now when we are comparing two holes made at H1 and H2 such that they are having equal range, okay, R1 is equal to R2. So this condition, what it is telling us that, H1 into H minus H1 is equal to H2 into H minus H2. So it's telling us that either H1 is equal to H2, which is not the case, or otherwise this quantity is equal to this quantity, and therefore this becomes equal to this. Okay. So H minus H2 is equal to H1, which is the same thing as saying that H minus H1 is equal to H2. So the product of these two is equal to the product of these two. You understand? So if this is equal to A and this is equal to B, here this is B into A. So that's
Yes,
how we are
sir.
getting that H is equal to H1 plus H2 by 2. I mean, H is equal to H1 plus H2.
Yes, I got it.
Now this we know as a separate thing, no? That maximum range will be equal to H. This we know from maximum minimum. That the general formula was 2 times square root of y into H minus y. So the maxima of this is 2 times square root of the maxima of this thing. So if we think of this as a function, you'll see that the maxima of this function is actually equal to h square by 2, and it is for y equal to h by 2. So the maximum range actually comes out to be h. That is how we get this result, that maximum range is h, and then h has to be substituted in terms of h1 and h2. So sorry, the maximum range is actually h1 plus h2, but the hole has to be cut at a position, and for this y should be equal to h by 2. Right, so Jagannath, this is clear now, this step also.
Yes, sir.
Okay, let's move on to question 54. Same exercise. Here a cylindrical vessel whose cross-sectional area is 1000 centimeters square given to us, fitted with a frictionless piston of this much mass, filled with water completely. Small hole of cross-sectional area is opened at a point 50 centimeters deep from the top surface. Velocity of efflux. Okay, so this is like slight variation of the standard speed of efflux derivation, because in that what happens at the top surface of the liquid, the pressure is, it's an open surface, so the pressure is equal to atmospheric pressure. But here that will change because there's a piston. So the weight of the piston will contribute to the pressure at the top surface. So this is a piston of mass m, cross-sectional area A. This depth is y. So again, what you do is you take this as 0.1 and just outside this as 0.2. So what will be the pressure at 0.1? Pressure at 0.1 will become atmospheric pressure plus mg by E because of the weight of the piston. Is clear, na, Shikhar?
Yes, sir.
Whereas pressure at 0.2 is P naught. Okay. And again, E into V1 is equal to small a into V2. So V2 will write as efflux velocity, and V1 will be A upon A times efflux velocity. So V1 is small compared to V2. Okay. So now apply Bernoulli's equation. So you get an extra term. It will be square root of 2gh plus some term. That extra term will come because of this additional pressure because of the weight of the crystal, mg by A. Understood? No?
Yes, sir.
So V1 plus half rho V1 square plus rho g h1 is equal to P2 plus half rho V2 square plus rho g h2. So V1 and V2 will substitute like this. Okay. P1 and P2 like this, and also we have h1 minus h2 is equal to y. So solving this, we will get just a second. Yeah. This kind of a term. Okay, so Shikhar, this is also clear.
Yes, sir.
Positive sign on the right hand side. So this is after substituting V1, V2 and all. So that's why this is come with a negative sign, because this is actually half rho V2 square minus V1 square. And V2 is efflux velocity, V1 is this. Understood, na, Jagannath? Why this is like this? Okay, next. Any other question from the module? Okay, so I'm assuming doubts are clear for fluid mechanics then. So coming back to properties of matter then. So let's do an example problem then. So we have a metallic rod. Young's modulus Y, area of cross section A, and natural length L, and mass M. Now we are applying forces like this, F1 and F2. So given so if F1 is equal to so 20 newtons and F2 is equal to 4 newtons, then find the elongation of the rod. So what you'll understand here is because F1 and F2 are not equal in magnitude, F1 is quite a bit larger, so the rod will be accelerating towards the right. It's a heavy rod which is accelerating, so it will have a variable tension. Okay, Parth, I will come to your question in fluids. Let's work out this question, then I'll come back to that one. So just try out this question, people.
Sir,
So you'll realize that the acceleration first of all you'll have to calculate the mass. So once you calculate this acceleration, you can now find the tension at any random point inside. Like, for example, if you want to find the tension at this point P, which is at a distance x from this side. So you can make an FBD of that much part. So from this you will get that the tension at any point at a distance x is F2 plus this tension is 4 newtons plus 16 by 5 into x. X is in meters, tension is in newtons. So from this you can see the stress is also linear. Now since the stress is linear, so what you can do is you can use the trick that stress is a linear function of x. So therefore, average stress is arithmetic mean of maximum and minimum. You can avoid the integration step. So maximum is when x is equal to 5 meters.
So that should be 2 plus 1.6x, right?
Yes, sir, 1.6. So you can go with this trick also, that the average stress is like this. So the strain is the average stress divided by Young's modulus. So delta L will be this much in meters. Okay. Or what you can go is what you can do is a more lengthy method of integration. So at a position X, if you consider a differential element, which because of this acceleration is under elongation, like this. Then for this you can apply strain is equal to stress upon Young's modulus. So this stress was this value. Young's modulus was so when you do this, you get the same.
Sir,
Yeah,
can you please minimize it?
yeah. This power here is wrong. No? This will be
Sir, -6.
micrometers में आएगा.
Sir,
Yes.
sir, I had a question, sir. So that, sir,
Yeah, tell me, Beta.
sir, how to identify the stress is uniform or non-uniform? Sir?
How to identify?
So the stress is uniform or non-uniform throughout the rod?
Heavy rod can always have non-uniform stress if it is accelerated. Whereas massless wire or massless thread kind of thing will always have uniform tension.
Okay, sir.
So heavy rod will have variable stress in two situations: if it's accelerated or if it is in a vertical position. So its weight is contributing to tension. You understanding now?
Yes, sir.
So these two situations it will have variable tension.
Sir, means the if the rod is massless, then it will have uniform tension. Sorry, uniform stress.
Uniform stress, uniform tension. Yeah.
Okay, sir.
Okay, so Parth, let's come to your doubt. Exercise 1, question number 23. That is of fluids. Just a moment, I'll go through the question. Okay, so given that a ball of relative density 0.8 falls into water from a height of 2 meters, the depth to which the ball will sink. Okay, so basically this is, you have to understand kinematics. And for the kinematics, the acceleration you have to calculate. So when it comes to the motion of the ball underwater, it will actually be a decelerated motion because buoyant force will be more than weight. So let's say this is the surface of water. Density of water being 1 gram per cc. Now this is the ball and it is made of material which has density 0.8 gram per cc. So starting from rest at a certain height. So as it's falling through this, it will have an acceleration of g. By the time it reaches here, its velocity is, let's say, v1. So this height is h. Now once it goes underwater, what will happen is it will have a deceleration because the buoyant force is greater than the weight. So underwater, buoyant force minus weight is equal to deceleration. So density of water into whatever volume of the body into g minus density of that material is equal to density of that material into v into k. So v is its volume. Okay. So you can see that this deceleration will be equal to this much. So deceleration will be g by 4. So now wherever it goes to the maximum depth, its velocity will become 0. So that's depth is d, let's say. So d will be v1 square by 2a. So it will be 2gh by 2 into g by 4. So this depth will become 4h. So this is exercise 1, question 23. Okay, good part. So let's pick up another example from variable stress concept. So this is very similar to the example we had done earlier in class, but there it was a rod hanging under its own weight only. Now there is also a block attached at the bottom. So this metal rod is of Young's modulus Y, natural length L, area A and mass M. Now this block has a mass of 4 times the mass of the rod. So we want to find the elongation. Yeah, so here also we can use that trick that if you see the tension at the top over here, it will be the total weight of the system, which is like in this case 5 mg, and the tension at the bottom here, which is just the weight of the block, so it is 4 mg. So at any point like this, at a distance x, it will be actually like this. So it will be, sorry, I have to take x from here. This kind of tension. So stress, so once again we can see that stress is linear with respect to x. So average stress method if you use, because it is linear, it will be arithmetic mean of maximum and minimum. But remember that you can use this average method only when it is a linearly varying function. So this method, or otherwise you can express stress as a function of x. You've already done actually. So take that element, and then you integrate. So what's this? Okay, so yes, very good, Shivam. That's correct. So in all these cases where the you have variable stress, typically the stress is because of the weight of a hanging rod distributed over its length, or because a heavy rod is horizontally accelerated, so you have pseudo force instead of weight acting, but in a distributed manner. So typically it will be a linear function. So in the case of a linear function, you can avoid the integration step, and you can just take average stress and equate the strain as average stress divided by Young's modulus. So delta L by L is average stress divided by Young's modulus. So that's a good shortcut trick you can use. Okay. All right, so I think with the examples we've done of fluid mechanics today, you should be well prepared for the test coming up on Sunday. Just make sure that you go through all the derivations, including one thing I noticed we did not cover in the doubts today, but it's very important, is the case of pressure gradient in an accelerated tank. Okay, so just remember that formula tan theta is equal to A by G in case of horizontal acceleration, and horizontal pressure gradient coming because of pseudo force, along with vertical pressure gradient coming because of weight. Okay. So make sure you revise that portion from the notes very carefully, and I think you should be fine with fluid mechanics. So that's it for today's session, people. Thanks for attending. Next week we'll again pick up properties of matter. We are almost done with properties of solid. Just one more definition of Poisson's ratio. That will take just a few minutes, and then we'll move on to properties of fluids, non-ideal fluids, that is viscosity and surface tension. So that will be the portion for the next week coming up. So that's it for today's session. Thanks for attending and wish you all the best.
Thank you, sir. Bye, sir.
Okay, bye people.
Thank you, sir. Bye.
Bye people. Bye.